Hello everyone, I'm Aditya Pandey, a PhD candidate in Northeastern University, and the title of my talk is Task and Data Consideration for Design and Recommendation of Tree Visualizations. I started my data viz journey in 2014, and ever since then I've had the opportunity to collaborate with people from many different backgrounds and work on a lot of interesting visualization problems. One thing that I would like to highlight about my career is the interchangeable role of being a practitioner and a researcher. My background as a visualization practitioner has strongly influenced my research direction. As a practitioner, I've always been overwhelmed with the available design choices for creating a visualization. An annual survey by the Data Visualization Society found out that the problem of large design space affects the broader visualization community. In this word tree created from the survey responses, we can see that practitioners have expressed their concern by saying that they have limited time to learn and explore new visualizations. Yet another challenge I faced as a visualization practitioner was the lack of availability of resources to help me design and create visualizations. Similar to the previous challenge, the survey showed evidence that due to time constraints, visualization practitioners are concerned about the effectiveness of their designs. That is, they feel that they're not doing it right or correctly. The challenge of large design space and limited guidelines is giving rise to this gap in visualization theory and practice. Researchers are creating new methods and techniques to visualize data, but there's little evidence on how much of that is actually percolating in practice. Over the last few years, there has been a significant effort from the visualization community to bridge this gap. Researchers have created theoretical resources like design frameworks and process models to allow designers to think more systematically about their design choices. On the more practical front, there are exploratory websites that provide prescriptive guidance to the designers on how to use and choose a visualization. And last but not the least are tools like Tableau and Voyager that are taking these guidance and converting them into practical recommendation systems. When we talk about design choices of visualization, it is very important to scope the conversation because visualization is an extensive field on a constant rise. Within visualizations, I want to discuss more specifically about tree visualizations. In my opinion, tree visualizations are special and important because of their ability to represent hierarchical information. Hierarchical organization of data has been the backbone of many scientific discoveries and modern technological advancements. Moreover, we can see that tree visualizations are widely applicable and they're being used in different domains like evolutionary biology, public health, finance, etc. The utility of tree visualization creates a lot of demand for it, but as a practitioner, choosing the correct tree visualization is extremely challenging because of the massive design space tree visualization has. As a result, I turned to the resources discussed earlier to identify how much do they support design of tree visualizations. Unfortunately, I found out that they have very limited support when it comes to designing tree visualizations. I found that limitation as an opportunity and consequently derived my thesis research question. The question is as follows: how can we develop theory, identify visualization best practices, and build applications that enable visualization practitioners to create expressive and effective tree visualizations? I broke down the overarching research question into three separate research problems. First, I learned and applied design study methodology in a number of visualization projects and retrospectively analyzed shortcomings or challenges I faced in the methodology. Next, I used the challenges as an opportunity to enhance the existing theory for design of tree visualizations, and in the process also surveyed and collected guidelines to inform design of tree visualizations. Finally, I used the knowledge created in the process to create practical recommendation systems. At a high level, the contributions of this thesis include development of novel tree and network visualizations for medical science, personal informatics, and cybersecurity, identification of tree visualization specific gaps in the design study theory and extension of the theory, survey of guidelines to select tree visualizations based on tasks and data, and design and development of novel recommendation systems for visualizations. Design studies are a visualization method for creating tools that support complex real-world data analysis problems. The nested model of visualization design was developed by Tamara Munzner to assist practitioners in their efforts of conducting a design study. The core part of visualization design study is the three-part design framework that acts as a scaffold for designers and practitioners coming from different backgrounds to think about their design choices systematically. Our goal was to test whether the existing theory supports design of tree visualizations. We tested the theory by conducting two design projects. First project was FreeBrovis. In that project, we developed a layout to visualize cerebral arteries. The next project I worked on involved visualizing servers in a data center. The ability to visualize individual workloads in an hierarchical format allowed the domain users to see patterns and anomalies in their communication traffic. Overall, both studies benefited from the existing design study theory, but the exercise of data and task abstraction revealed that existing theory needs more work for tree visualizations. One of the shortcomings that we found was the lack of task abstraction specificity in the Y part of the framework. The existing task abstraction does not provide enough categories to correctly distinguish between two tasks. In CerebroVis, to solve the problem, we had to use network task taxonomy by Bongshan Lee, as highlighted in the figure. Even though network task was not specifically designed for tree visualization, it provided a more accurate abstraction of tasks. Why do we care about task abstraction specificity? As we can see, without proper task abstraction, all the tasks are categorized in a blanket category. Therefore, information is not sufficient to allow practitioner to make a decision about visualization encoding, which defeats the main purpose of task abstraction. To extend the task abstraction theory, we surveyed tree visualization tasks from published papers. We performed a meta-analysis of the tasks to recognize ways to improve the abstraction specificity. We found that the limitation of theory was due to the shallow treatment of tree visualization targets. As a result, we contributed a more extensive list of tree visualization targets as shown in the figure on the far right. The tasks that we saw in problem 1 are now being abstracted with the new theory. As we can see in the figure, the extension leads to more accurate task abstractions and the visualization choice. A byproduct of our survey was empirical data that can be used to build design guidelines for tree visualizations. Through the Design Guidelines project, we aim to create an exploratory resource for the practitioners to get information about tree visualization design based on the task and data requirements of the users. The third part of my thesis builds a recommendation system by using the design guidelines identified in the survey. I will first discuss my ongoing project where I'm building a recommendation system for genomics visualization. Then I will discuss how my experiences working with genomics visualization will translate to development of a tree visualization recommendation system. Genomics is an interdisciplinary field of biology focusing on the analysis of structure, function, and evolution of genomes. In a comprehensive survey of genomic visualizations, my collaborators, Sabrina, Teresa, and Niels, identified that there are a large number of techniques to visualize genomics data. As a follow-up to the survey, we asked practitioners how do they choose visualization tools for analysis. We found out that practitioners primarily take into consideration their familiarity with the tool, the features of the tool, and the effectiveness of the visualization encoding are more of a secondary concern for the practitioners. Based on the feedback, we concluded that a recommendation system may prove beneficial to the practitioners and expand their search for genomics visualization tools. I was particularly interested in this project because the knowledge or recommendation rules for selection of genomics visualizations were already curated by my collaborators in their survey paper. Therefore, I was able to focus on the development of recommendation system and bypass the process of curating design guidelines. In the current form, the genomic recommendation system accepts the data and task specification of the user and maps it to the different parts of visualization taxonomy to identify an appropriate visualization output. For tree visualizations, we are trying to replicate the methodology that we use for genomics visualization. The core idea remains the same. The user will be able to input data and task specification, which will then be mapped to tree visualization design taxonomy. Using the recommendation rules, the most appropriate visualization will be suggested. However, there is still an open research question which can make the task of developing tree visualization recommendation system non-trivial. Unlike the genomic visualization, the visualization taxonomy of tree visualization is not well defined. There has been prior work where researchers have defined tree taxonomy based on dimensionality, alignment, or space usage techniques, but more work needs to be done in this space. We care about the taxonomy because having a clear visualization taxonomy was beneficial in building genomics recommendation system. We were able to identify empirical guidelines for each part of the taxonomy and use the sequential nature of visualization design to identify the most appropriate visualization technique. Since the design of tree visualization taxonomy is still an open research question of my work, I would like some recommendation or suggestions from the panel on how to approach with it. Another open question in the recommendation system research is the selection of evaluation methodology. Currently, I identified three methods to validate the recommendation system. A controlled lab study where a group of participants familiar with tree visualizations will report their experiences. In the long run, I would like to release the tool to the community and see factors like adoption. The third method can be application of the tool in a classroom setting. The idea is to use the recommendation system for student projects. I'm particularly excited about this method because it simulates a real-world scenario and fits very well with the intended audience of the recommendation system. Over the years, I've had the opportunity to apply my research, design, and engineering skills in the domains of cybersecurity, medical diagnosis, genomics, and manufacturing. Out of all the domains, my projects in biology and medicinal sciences have excited me the most. As a result, after graduation, I want to find a job in the industry or in a research lab where I can work at the intersection of biology, medical diagnosis, and visualization. Right after my graduation, I also want to apply for a postdoc position to enhance my research portfolio. Before I end my talk, I would like to thank my fantastic thesis committee, as none of this work would have been possible without their support. I will also like to acknowledge the organizations that have funded my work. Finally, to kick off the discussion, I've listed some questions for the panel.